Hi everyone, welcome to lesson 2. So in lesson 1 we talked about translations, which is when you slide your graph up or down or left or right. And now we're going to be talking about dilations, which causes your graph to grow or shrink, or like get larger or get smaller. So specifically, we're going to be talking about vertical dilations and also horizontal dilations, just like how we talked about vertical translations and horizontal translations. So when we are talking about a vertical stretch or compression, your K value is being multiplied by your entire function on the outside. So basically, what we are doing when we're doing a vertical stretch or compression, we are stretching our graph vertically related to the y-axis. So if I take this dog and I stretch it vertically, if I stretch it up and down, or if I stretch it up like this, the dog is getting taller, but it's getting more narrow, as opposed to if I start to stretch it down or compress it, the dog is getting shorter but also wider at the same time. So a vertical stretch would cause the graph to get taller, but cause the graph to also get a little more narrow. For example, if we look at the orange graph here, this is the parent function of an absolute value function. If I were to stretch it, you get the green graph, which now becomes more narrow and it's going to get more tall. If I do a shrink, remember, the dog gets shorter but also gets wider. So a shrink causes the graph to get shorter and wider. For example, if I look at my graphs here, the orange graph compared to the blue graph is when I compressed vertically down and I got a wider and shorter graph. So basically, imagine taking a graph and pulling it or stretching it up vertically or pushing it down vertically. That would be a vertical stretch or compression. Now, on the graph, how you find your new values, your new ordered pairs, is your x value would stay the same on your ordered pairs, but you would multiply your y value by your dilation here, your k value. A k value that's greater than 1 will cause your graph to stretch, whereas a k value that's in between 0 and 1 would cause your graph to compress or shrink. Now this is for vertical dilations. Horizontal dilations, just like horizontal translations, are the hard ones to remember. A horizontal dilation actually is the opposite of what you think. If your k value is greater than 1, that's actually going to cause your graph to compress or shrink. Whereas if your k value is in between 0 or 1, it causes your graph to stretch. So it's the opposite of vertical compressions or dilations or stretches. But remember, just H is the horizontal ones are the hard ones to remember. So that's an easy way to remember that it's the opposite of what your mind thinks. Now we are taking a graph and we're pulling it out horizontally or pushing it in horizontally. For example, if I were to take this dog and pull it out horizontally, that would actually have a k value that is greater than 1. That has a k value in between 0 and 1, I apologize. And it causes the graph to get more wide. As you can see, the dog's getting wider and wider and wider. As if you are pushing, if you're shrinking or compressing it in, this would be a k value greater than 1, and the dog gets more narrow here. So that's what I mean when I'm doing a horizontal stretch or compression. When we are doing a horizontal stretch or compression, what we do is we multiply our x value by the reciprocal of k. And our y value actually is the one that is left alone. So we multiply the x value by the reciprocal of k and leave y alone. Now vertical stretches and compressions and horizontal stretches and compressions are actually easier to see with a graph called the step function. This is an example of a step function. It's just it's a disconnected graph here that looks like a series of steps. And if we were to do a vertical stretch, we could expect these steps to get further apart vertically from one another because we're stretching this graph vertically. So if we look at this graph here, if I do a vertical stretch, this is what my new graph looks like compared to my old graph. So you could see the blue steps are stretched further away from one another compared to the red steps. That is what I'm talking about stretching vertically. If I'm talking about compressing vertically, from my original graph, we would shrink our graph down vertically, meaning that the steps would get closer to one another. So looking at the green steps compared to the red steps, the green steps are much closer because I did a vertical compression. So vertical stretches are when your K value is greater than 1 and your graph gets vertically further away from one another. The steps here would get vertically further away from one another. And a vertical compression is when your K value is in between 0 and 1 and your steps actually get a lot closer. They come closer to one another. We're compressing the graph vertically. Now I'm going to show you what a horizontal stretch and compression would look like. A horizontal compression is when your K value is greater than 1. And basically what that means is if we're doing a horizontal compression, all these steps are going to get shorter because we're pushing all these steps in horizontally. So if I have a K value greater than 1, that's going to cause the graph to horizontally be compressed. So the steps will be shorter. Look at the purple steps compared to the red steps. They are shorter than the red steps because I did a horizontal compression. And notice my horizontal compression, my K value was greater than 1. If I do a horizontal stretch, your K value is in between 0 and 1. And what this is going to look like is it's going to look like your steps are getting longer. We're taking each of these steps and we're stretching them out horizontally because we're doing a horizontal stretch. And if we look at the black steps compared to the red steps, we do see that each of these steps grew by a factor of 2. But my K value here was in between 0 and 1. So the horizontal stretches and compressions are the difficult ones to remember because if your K value is greater than 1, you would think it would be a stretch, but it really is a compression. And if your K value is in between 0 and 1, you would think it would be a compression, but it's really a stretch. All right, vertical stretches and compressions are exactly what we could picture them to be. But I wanted to make sure that you understood that that example here. So now we're going to look at reflections. If I have a reflection in the x-axis, let me actually show you what happens. So let me start back with my dog upside right, or right side up. Okay, if I have a negative on the outside, what that means is I'm doing a reflection over my x-axis. So this dog would just flip upside down, like so. Now, when we are doing a reflection in the x-axis, if we look at my graph here, this graph had an x, the top point had an x value of 2 and a y value of 2. In my blue graph, now I have an x value of 2 and a y value of -2. So when we are looking at points, the only points that change are my y values. And so my x stays the same, but my y value becomes the opposite sign of what it originally was. That's a reflection over the x-axis. Now let me get this dog back the right way here. If I have the negative on the inside of my parentheses in my f of x function, this is a reflection in the y-axis. So I would take my dog and I would just flip it over my y-axis and it's going to look like this now. With parabolas, it's kind of hard to see. However, what we did here was we took this red point, which is the point -2, -2. we reflected it over the y-axis to get this point here, which is 2, -2. So what happened was my x value now became the opposite and my y value stayed the same. So that would be a reflection in the y-axis. Now we're going to move on and we're going to do some example problems. And remember, horizontal stretches and compressions are the most difficult ones to remember. Number 1, I have the negative on the outside of my f of x function. So if you go back to the chart, you can see that when the negative's on the outside, this is a reflection over the x-axis. So my x-axis is this here. If a point lies on that x-axis, then it stays where it's at. But this green point here is going to be reflected over the x-axis like so. And so now I'm going to have the new graph look like this with every point reflected over the x-axis. So that would be graph number or letter C here. Moving on. We want to write a rule for the transformation described by the parent function y is equal to f of x. Now we need to be careful. Your compressions are always going to be listed as whole numbers. Or sorry, your stretches and compressions are going to be listed as whole numbers. But in your equation, it might not look like a whole number when you represent it as an equation. For example, a vertical compression means that your k value should be in between 1 and 0. So if I say that my vertical compression is by a scale factor of 4, that actually means my k value is 1/4. So my vertical compression would look like this in an equation format. Y is equal to 1/4 times f of x. Now in the next one, a vertical stretch would mean that your k value is greater than 1, and we have by a factor of 4, so my k value is going to be 4 because 4 is greater than 1. So my vertical stretch in the format of the equation would look like the following. Y is equal to 4 times f of x. So those are vertical stretches and compressions. Now horizontal stretches and compressions are what we're going to be dealing with in numbers 4 and 5. So 1, a reflection over the y-axis means that your negatives on the inside of your f of x. And then be careful on this, horizontal compressions are the hard ones to remember. Now a compression, you would think the k value would be in between 0 and 1 because you would think it's getting smaller. However, with horizontal compressions, my k value is actually greater than 1. And so my horizontal compression by a factor of 3, my k value would be 3. And that's it for that one. Now a horizontal stretch by a factor of 3. Since it's a horizontal stretch, that's the hard one to remember. A stretch you would think would be your k value would be greater than 1, but actually your k value is less than 1, but greater than 0. So by a factor of 3 actually means in my equation, I'm going to have a 1/3 as my k value. And that is my correct equation. Now for numbers 6 through 9, we're going to describe the transformation and then name the point after each transformation. In number 6, with the 3 being on the outside, on the inside, this is a horizontal compression by a factor of 3. And I'm going to give you the rest of them first before we find the points. When I have a 1/2 on the outside, that's a vertical compression by a factor of 2. A negative on the inside of parentheses is actually a reflection over the y-axis, where a negative on the outside is a reflection over the x-axis. Now we're going to use the rule for a horizontal compression. What we do is we do x times the reciprocal of your k value here. So that's going to be a 1/3. The reciprocal of 3 is 1/3. And then we leave our y value alone. So my x value times 1/3 is a 2. And then we leave my y value alone, which was a 1. Now for the next one, for number 7, you leave your x value alone and you do your k value times your y value. So I have my 6 and then a 1/2 times a 1 is a 1/2. Now for number 8, just your x becomes the opposite of what it is, and number 9, just your y value.